Okay. So let's see, today I'm going to have a challenge of keeping everybody awake even more than yesterday because we are further down in, through the day. So I will start where I left off yesterday and see how far I can go. In yesterday's lecture was more pedagogical in terms of example calculations of Fisher information, what its meaning is, and how we could do ground up calculations of Heisenberg limits and so forth. Today's lecture will be a little bit more of a seminar colloquium style lecture where I will be applying those tools that we talked about yesterday, but we'll be looking at a variety of different examples of photonic sensors and actual sensors that ties to experimental realizations of useful applications. So this is the slide where we stopped to take questions yesterday. And before this slide, I'll go one slide backwards for a moment. Here is the slide where we discussed how if I had n atoms and each one was subjected to the same field, that preparing the atoms in this GHZ state can get you the Heisenberg limited sensitivity. And you had seen this example in multiple talks in the last few days. Now, one of the things that happens is that there's a variety of different situations where you can imagine you have a bunch of sensors that are trying to sense the local field. It could be a magnetic field, electric field. And what you care about is not estimating those fields themselves. What you care about is some function of those individual local fields that you want to estimate. And in the previous example, what did I say? There's that same theta that is modulating all the atoms. So if the thetas that are modulating all the atomic sensors are different, but highly correlated, but what you were interested in is not the theta, but some function of those thetas, in those situations also, entanglement among those atoms helps. Okay, so this field started with some papers not that long back, I would say 6 years or so. And since then, there has been an explosion of papers in this whole area. And I would point out only a few references here. If you're interested, I would suggest take a look at Alexei Gorshkov's group's website. He is in the University of Maryland and has been doing a lot of this work. In fact, I stole some of the pictures from some of his papers. So the Hamiltonian looks the same, except that the different thetas are different. And you are interested in some parameter. And in this situation also, he showed that this GHZ state, when you are interested, let's say an average parameter, your Q is the average of the parameters, GHZ state is optimal. But what happens is that when your parameter of interest changes functionally in terms of the thetas, the optimal state in terms of what maximizes the QFI, it also changes. So there has been a lot of interesting work in the more recent years on multiple parameters embedded in those thetas. So you have still n sensors, let's say you're sensing a magnetic field, but you're interested in, say, a small number, maybe 3-4 different parameters. What could be an example situation of that? So let's say that we heard about imaging magnetic fields for ECG measurements, like you're looking at heart signals. You're trying, that generates a tiny femtosecond per root hertz kind of magnetic field. You're measuring that. You don't care about the magnetic field. Let's say you want to diagnose an irregular ST segment defect in your ECG. And you are doing a hypothesis test. Is that defect there or not? That's the type of thing where entangling the sensors that are looking at that overall correlated field helps. And there are many more examples you can come up with like that. But if there are multiple parameters, then there are interesting techniques in Bayesian estimation theory where you can even evolve the probe state as you are looking at these parameters from one trial to the next and so forth. I'm not going to go into the details of this. What I will spend instead a little bit of time on is to how do you generate entanglement between atomic qubits? And I wanted to talk a little bit more about atomic qubits because Kasturi told me that there'll be talks that will focus more on the experimental side of things. So let's transition and talk about a defect center in diamond. And then I'm going to come back and talk about some examples in photonic qubits. So let's take a pause from what we have learned. We are going to talk about how do you generate entanglement among spin qubits. So what I'm drawing here, this is the diamond lattice, carbon lattice, tetrahedral lattice. And this is a picture of a silicon vacancy color center. This is a term you would hear a lot in the literature. People will call it a solid state defect center, color center defect in diamond, silicon vacancy color center in diamond. They're all the same thing. Two neighboring carbon atoms in the lattice that are missing, that is replaced by a bigger silicon atom. And there's a free electron on that silicon atom whose ground state serves as the qubit. What you do is that there is an external magnetic field that splits the ground state into what is it, a tens of gigahertz? So this forms your qubit, the up and the down state. And obviously the first excited state also gets split into two levels. For silicon vacancy color centers, the gap between this down and down prime is roughly 737 nanometers. Okay, so this transition, you can initialize the silicon vacancy qubit in the down state, in the ground state, and then experimentally you can apply a microwave pulse to do arbitrary rotations between the down and the up state here. So one way in which people have looked at generating entanglement among that spin qubit and a photonic qubit is that you start by initializing the qubit in the equal superposition state, up plus down by √2. So these two zeros, ignore them for now. These two zeros are just presence or absence of a photon in two time. So there is no photon right now. So it is just up plus down by √2. Then what you do is that you hit the atom with a strong laser pulse at 737 nanometers. So what happens when you hit the thing with a 737 nanometer? The population in the down state, this down, it goes to down prime. And then when the pulse goes away, then the down prime spontaneously decays back to down. But when it decays back to down, it emits a single photon Fox state, one photon emission that I talked about in the previous lecture. But then the up never makes it top prime because this is slightly detuned away from 737 nanometer. So what happens? Only the down emits a photon in that first time bin and nothing comes here. So now you have an entangled state between the spin and the presence or absence of a single photon in one bosonic mode, which has a name. It's called the single rail photonic qubit. Is that clear? So single rail photonic qubit is a way to encode a single qubit by presence or absence of a photon in one mode, one temporal mode. Now, something interesting that people would do is that you would repeat this process, but then first, before that, you apply a microwave pi pulse. And what it does is that this microwave pulse applies a NOT gate. It flips the sign. So the qubit, the up becomes down, the down becomes up. And then you apply another strong laser pulse. Okay, so now what will happen is that this down is going to emit a photon because we'll go to down prime and emit a photon and come back to down. And the second time we'll have a photon over here. So you will get, but the second time bin over here will not get a photon because this is in an up state. It never makes that transition. And what is this state? If you look at this state, this is a state that is a bell-like state, an entangled state between a single spin qubit and a dual rail photonic qubit. What is a dual rail photonic qubit? When you encode a qubit by placing one photon in this mode versus one photon in that mode. You have two modes, two orthogonal time bins in this case. One photon here, no photon here is the qubit state 0, one photon here and no photon here is qubit state 1. And this particular encoding is particularly useful for photonic quantum computing using linear optics. All right, so no matter which form of encoding you are using, I'm going to denote this by this box that this is a spin qubit, this is a matter qubit, and this is my photonic qubit. This could be a dual rail or a single rail, doesn't matter. You can deterministically, in principle, excite an atomic qubit to generate a photonic qubit entangled with it. Is that clear? Okay, so once you do that, then the next step that people do is that they would do that on two sides. So you have an atomic qubit generate a photonic qubit, and maybe another atomic qubit sitting at a distance emit a photonic qubit, entangle with it. This is in a Bell state, that's in a Bell state. And then you take the two photonic qubits, they fly into a beam splitter, and they meet on this beam splitter, and you do a detection event here. Now, depending upon whether it's a dual rail or a single rail, you will herald based on two different click patterns. So for the single rail case, you just look for click, no click, or a no click click. One of these two options, if it happens, then you say that I have a successful Bell state measurement. And if that Bell state measurement succeeds, then what you do is that you have an entangled state among the two spin qubits. So the photonic qubit dies, the two spins are entangled. And then you can look at how good is that entanglement. Okay, so my student Prajit Dhara, he calculated in that particular paper. So if you look at this I of rho AB is the density operator of this two qubit state. I rho AB is the amount of entanglement in that one copy of the spin-spin entangled state. What do I mean by amount of entanglement? Meaning if I give you n copies of that state, you can generate n times I number of perfect Bell states from that if both sides had access to arbitrarily powerful quantum processors. and I is obviously less than 1. So n goes to n times I. That I is called the distillable entanglement of that state rho AB. A very simple quantity to calculate the lower bound to rho to that I, and that so I of rho AB is called the distillable entanglement, and the physical meaning of that is that if I have n copies of this rho AB, if I have a fully powerful quantum processor, and let's say I measure off some of the qubits, and I left over with k qubits here and k qubits there. These k qubits are in perfectly entangled state. So I'm going from rho AB n copies of that to a perfect Bell state with k copies of that. K over n is called the distillable entanglement of rho AB, maximized over all possible local operations in classical communications. This quantity is usually hard to calculate, but what you can calculate is a lower bound to that. So there are two lower bounds that are very well known. This is called the hashing inequality. S is the von Neumann entropy of the density operator, negative rho log rho. If you want to calculate this quantity, it is nothing but the Shannon entropy of the eigenvalues of rho. PIs are the eigenvalues of rho. And similarly, this quantity is also a lower bound to the distillable entanglement. A lower bound means that this quantity is an achievable quantity, meaning if I calculate this, one of these two things, I can design a quantum circuit such that as n increases, I can actually distill these many qubits. So this process is known as entanglement distillation. If I give you noisy entangled states, how do you extract good quality entangled states from it? Prajit also multiplied, as you see, this with a probability of success, because this is a probabilistic process. So the y-axis here is the rate at which you can generate entanglement as a function of loss in the channel. And there are a few things here that he considered, for example, detector excess noise that causes this rate to sharply drop, mode mismatch in that interferometer to get a 0.95 or something that will drop the rate. And then a carrier phase mismatch between the two photons, which only affects the single rail case. So that's why people don't use the single rail encoding. The dual rail encoding is much more robust. All you need is a good phase mode mismatch here. So even though the dual rail qubit has a worse scaling in terms of loss, it is much more robust to noise and and mode mismatch. Okay, so after this, then you may ask that, okay, I have generated entanglement between two atomic qubits. If you let it sit inside, let's say, a cryostat. By the way, these qubits, silicon vacancy color centers, if you wanted to do this experiment of have it emit a single photon, they will have to be sitting at roughly 100 millikelvin. 100 millikelvin, the only way to support that right now in current technology is something called a dilution refrigerator. That thing costs close to $1 million. It's a very, very expensive equipment. Misha Lukin's group at Harvard University, he just last year, I forgot to cite his PRL here, his group along with Marco Lonkar, they actually showed the spin-spin entanglement demonstration in two silicon vacancy color centers for the first time using this method. Now, if you let it sit inside a cryostat at a given temperature, this distillable entanglement is going to go down because the state is going to worse and worse. So what Prajit calculated through a very detailed master equation study of a phonon-induced decoherence mechanism, and this thing is not working, I don't know why. Let me just use my... Oh, it has progressed several slides, but it is not showing here for some reason. I don't have video. I think it has disconnected from Zoom. Oh, yes, I think. Anyway, I'll just speak to this slide for a moment. So okay, there you go. So the distillable entanglement is going to decay as a function of time, and the reason for the decay is that when these spins sit inside at some temperature, they interact with phonons. They are in a carbon lattice, right? And that interaction with phonon, that causes decoherence. So when you write, so in that paper that I was going to talk about, we modeled the decoherence, traced out the phonon modes, and then just again looked at rho AB, the two spin density operator, and see how that entanglement decays as a function of time. And that decay is, it's an exponential decay, and that this is the I of rho t, and the decay constant is a function of the temperature that you're operating at. Now, if you can generate entanglement between two spins, you can generate entanglement between any number of spins. Well, if you have, let's say, these color center spins connected to optical waveguides, and you can have photons that are emitted from them. They can be routed from any to any. So imagine you have a square grid of these color centers. You have each one of them can emit a photon. The photons can go meet with a photon from another emitter in different ways. You can generate large scale entanglement. In fact, if your success probability of these Bell measurements, they don't even need to be 1. They can be smaller than 1, but as long as they're above a certain threshold, you can still generate a long range connected entangled state of these atomic qubits. And this phenomena, that there is a sharp threshold of the probability above which you can generate a large long range connected entanglement, is called percolation theory. It's a very interesting sub branch of applied probability that one can use to generate these entangled states of many emitters, which can be used for quantum computing, quantum sensing, as well as building states for quantum repeaters, which we will not talk about in this talk, but there's applications across the board on these many body entangled states of these atomic qubits. My colleague Dirk Engeland's group has pioneered some of the large scale integration work of these artificial atoms in photonic circuits. Dirk and I are collaborating right now on generating these waveguide coupled color center systems to generate mini qubit entanglement, which we want to use for fault tolerant quantum repeaters for long distance entanglement distribution, for example. All right, now this process that I talked to you about of generating this entanglement between a spin and a photon, remember I did this 2 steps. I first generated the single rail, then applied the pi/2 pulse and generated another entangled state. I didn't have to stop at that second step. I could have just kept going after the second time bin. If I kept going, what would have happened is that you would generate entanglement between that spin qubit and multiple photonic qubits in a row. And such entanglement, it is called a cluster state. Again, some of you may have heard this term, some of you may haven't. But a cluster state is represented by a graph where every qubit you first initialize in this equal superposition state, and you do a control Z gate wherever you have an edge. And these cluster states are a useful resource for universal quantum computing, along with non-Clifford and Clifford measurements. But one interesting thing that happens is that if you can generate these 3 photon cluster states with a single atom, and then you can take these 3 photon cluster states. So these are, like, look at this. This is a 3 photon cluster state. That's a 3 photon cluster state. And these little blue circles and green circles I'm showing, those are Bell measurement attempts. Those are these 2 photons meeting on a beam splitter that I showed. Each one of those green and blue circles is trying to have 2 photons meet on a beam splitter, and lambda is the probability of success of that Bell measurement. Turns out that if lambda is above a certain threshold, so for this particular geometry, if it is above say 0.6, whatever, 0.67, it looks like here, then suddenly there's a constant fraction of the unmeasured photons in the middle. They are connected in a giant connected component. And now you may ask, what is the lambda that is achievable with photonic circuits? So I showed you this beam splitter method. So these 2 lines correspond to the 2 modes of one dual rail qubit. These 2 modes carry 1 qubit, these 2 modes carry another qubit. This Bell measurement succeeds with probability of success 1/2, maximum probability of success. So this is obviously 0.5 is to the left of the threshold. But there are circuits that are called boosted Bell measurements, which allow for additional ancilla single photons to be brought into a bigger linear optical circuit that can attain a higher value of lambda, higher than these percolation thresholds. Which means that if I can use these color centered emitters to generate even 3 photon cluster states, then you can generate a deterministically long range connected cluster states of the photonic qubits. Just like you could generate long range connected entangled states of atomic qubits as a sensor, these photonic entangled states could be used, for example, for all photonic quantum computing. There is a company based in Palo Alto called PsiQuantum, started by Professor Jeremy O'Brien and Terry Rudolph 5 years ago, or so roughly 6 years ago now. And they are building a photonic quantum computer using this method. Okay, so let's now talk about a couple of optical examples. Okay, so yesterday we talked about the squeezing enhanced sensors. And let me make you recall the example that we talked about. We had this Mach-Zehnder interferometer, if you remember. I had a θ/2 and a θ/2. And one of you, forgot who you asked me the question. I think you asked me the question whether we needed to have θ/2 and minus θ/2. I said no, you could have a theta and no phase in one of the arms. Okay, so let's say that each one of these things, like this square is 1 Mach-Zehnder interferometer, 1 MZI. This is another MZI, another MZI. Each Mach-Zehnder interferometer has a phase. I'm calling it θ 1 phi, theta 2 phi, theta 3 phi. So this little m index runs over the Mach standard interferometers. Okay, there are capital M of the interferometers. Each one is getting a different phase. But I don't care about the individual phases. I care about some function of the phases. Why so? Well, let's take one example. One example of this is an RF photonic antenna. So what is a radio frequency photonic antenna? This is actually a commercial product you can buy. These are microwave fields impinging on sensors, where the sensor modulates an optical phase that is proportional to the radio frequency intensity that is falling on it. Okay, so the people read out that optical phase using a laser. So they just put a, there's a laser, I'm just splitting it on a fiber splitter. These are just coherent states, and this is vacuum here. Now you might wonder, what happens if I inject squeeze vacuum here? Like, squeeze vacuum can give you better performance for sensing a phase. But then here, we are not even interested in the phases themselves. Who cares of the individual phases if all I am interested in is what is the angle of incidence of the microwave field? Or what is the center frequency of the microwave field? Or maybe there is a signal in the microwave field that is embedded. I'm trying to do a hypothesis test, some sort of a global question that involves those phases. In such situations, I already told you that entanglement across these help. But in this case, what kind of entanglement? Well, the kind of entanglement that helps here is that we talked about the squeeze vacuum yesterday. If you take a squeeze vacuum state and put it on a beam splitter, you get an entangled state at the output. Remember, if I put a coherent state on a beam splitter, you get a product of two coherent states. But if I put a squeeze state on a beam splitter, I get an entangled state. It's a Gaussian two-mode entangled state. So similarly, if I take a squeeze vacuum and split it on a multi-port interferometer, I'll get an M-mode entangled state. So if I put that entangled state into this, then you suddenly, with a linear optical interferometry after this and a homodyne detection to estimate, the phi, which is the parameter that I actually care about, not the thetas, you can get a huge potential improvement in the sense that the quantum Fisher information as a function of the number of sensors can grow as m squared as opposed to m in the lossless case. Just as usual, if there is loss, it will still scale as m, but there can be a constant factor improvement. If I use a product state, meaning if I inject just squeezing individually in each one of them, I will still get an improvement, but I will not get a Heisenberg scaling with respect to the number of sensors. So I told you already the RF photonic receiver example. In this case, the theta m takes this particular form, where this is the radio frequency intensity, and I could be, for example, estimating this angle of incidence of the RF field, and you get a pretty interesting improvement. And you can take a look at this paper here for these plots, but these plots showing this tau is the transmission parameter. When tau decreases, meaning I'm making my system lossier and lossier. And look at the blue and the yellow plot. The blue plot is the quantum Fisher information in the presence of loss. The yellow plot is the classical Fisher information for my receiver that I mentioned, which is this interferometer followed by homodyne detection. And set for tau equal to 0.9, the classical Fisher information of my receiver with the quantum state, with this entangled squeeze state being input, is still higher compared to the quantum Fisher information for a coherent state transmitter. Is that clear? So the quantum Fisher information is the best possible performance you can get for that transmitter. So if I use a laser transmitter, the quantum Fisher information is saying this is the best you can do. And even from that best, you can do better if I used an entangled state to be injected into those vacuum ports. So this was implemented by an experiment a few years ago by my colleague, Professor Jeshen Zhang at the University of Arizona. Take a look at his work. It's a very interesting result, and we are looking at extending it and applying it to actual systems. Okay, so let's talk about another example. So and remember, all these examples that I'm talking about right now, they all use the same underlying physics, but they are so very, very different applications. Atomic force microscopy. Have you heard about this term before? Okay, few people have heard about it. Very good. So, atomic force microscopy, the idea is that you measure a rough surface. You have a scanning tip. It's a cantilever that you scan across a surface. And as that scanning tip moves, you bounce off a laser. And as this moves up and down, the reflected laser does this. And you measure it with a camera. And from that displacement, you can estimate the roughness of the surface. So we are asking a very simple question. My student, Benhua, she looked at this question. She's saying, okay, if I take a diffraction limited propagation geometry, meaning I have an aperture, transmitter aperture, receive aperture, I have an object, And I just want to estimate a single linear deflection of a mechanical membrane. I just want to just estimate one parameter. What is the optimal state to use? So she did a full normal mode decomposition of this propagation kernel. And her parameter of interest is this one scalar parameter, this D, let's say this parameter, which is this displacement, one displacement. But now you have multiple co-propagating orthogonal spatial modes. When she did the math, the way this D, that parameter of interest, shows up in the actual field, it unfurls itself into exactly that array of Mach Zehnders with those phases that I showed. It was almost magical. So we could lift that theory and apply it to this problem. And unsurprisingly, she found that this taking a squeezed vacuum state and splitting it in a linear optical interferometer into the multi-spatial mode, co-propagating spatial mode entangled state across it over the first 4 or 5 Hermite Gauss modes gives you a sensitivity improvement in sensing the beam deflection. And right now we are working on an experiment working with a colleague of mine, Dal Wilson at the University of Arizona. Now, before she calculated the quantum state, she even asked this question about a classical state. So she said that as I increase the support of the number of spatial modes over which my classical probe beam lives, what is the QFI I'll get per photon for the beam deflection parameter? So this DF parameter is called the free space Fresnel number product. Transmitter area, receiver aperture area, center wavelength, the total transmission length. So when this number is larger than 1, you can pack in roughly DF number of co-propagating spatial modes with a very high transmissivity. So as you increase DF, the overall QFI keeps increasing to a larger number of total spatial mode support. And when she plotted what that more optimal mode looks like, it has this interesting bimodal shape, and that gives you, depending upon what DF value you are at, DF 90, which is the conventional, she worked out some numbers for commercial AFMs, that you could get a factor of 10 to 20 improvement in the sensitivity, even with an optimized classical beam. And here, it's all classical physics, but QFI was a tool for us to find the optimal classical transmitter. It was beautiful. And then she took that work ahead and found a quantum transmitter which lives over the support of the first 8 Hermite Gauss modes. But this one will require a squeezed vacuum source and something that I'm going to talk about a little bit more detail later called the multiplane light conversion device. It's a mode sorter. And this is like a beam splitter array that I'm splitting that squeezed vacuum onto. So this is now generating an entangled state across the first 8 co-propagating orthogonal Hermite Gauss modes of the propagating field. This is a spatially entangled state. And that gives us another some factor of 10 or so improvement over the best classical transmitter. By the way, feel free to interrupt me. Yes, there's a question right there. So can somebody pass the mic?
In the previous slide, you showed the coherent states and the squeezed vacuum entering the interferometer. So is it necessary for you to have them in the same phase, all of them, before entering the interferometer?
That's a very good question. It's a very good question. So you can ask the question. So for coherent state, I would say probably it doesn't matter, because if you know the phase, you can cancel out the phase on the receiver side. You can pre-compensate, post-compensate for that. This state, actually, we don't know what the optimal state is. Okay, and so this next slide that I showed, Venhua's example, so by the way, this is not yet published. This red line that she shows here, it is just a numerical optimization she did over the first 8 Hermite Gauss modes. And what she finds is the optimal state involves a single coherent state and a single mode squeezed vacuum split into a very complicated interferometer, which is not quite that equal phase splitting of a squeezed state that I showed in the previous slide.
Right.
So your intuition is absolutely correct. So, but then I don't have a very good answer to give. Like if you give me a lossless system, meaning if it's a lossless scattering matrix that encodes a single parameter, then people have proven that the optimal state involves a single mode squeezed vacuum split in a given interferometer, and there is a prescriptive way to find that interferometer.
Okay.
Lossy case, we don't know. That's an open question. And
Thanks.
If you're interested in that question, we can talk more about it.
Thanks.
Okay? Good. Any more questions? Can you use that mic?
Quick question. Okay, there we go. So quick question, Saikat. So this single parameter that is encoded, should I imagine that this is one of the pixels that you want to image?
No, just a mechanical deflection. I have a membrane. Okay, I have a membrane and
Okay.
I'm optical beam looking at the reflection. As I'm changing, this is my D, and my light is doing this reflected light.
So if you want to make an image which is complicated, like the first one there,
That is more complicated. I'll get to that. Yeah, very good question. So, but that's a good question though, Sai. So normally what people do is scanning tip, AFM, they just scan, right? But then that's a very interesting point, and I want to look at that question. What if I just want to do a wide field imaging? Okay, I don't want to scan the thing over that. It's very inefficient. No, as Kasturi would vouch for when she's looking at some papers in this area. Then it's an interesting question that now you can ask the question that I have a rough surface object, but maybe I'm doing a discrimination between some cells. Maybe you're looking for a cancerous cell. Maybe you have some information about the object. What is the right entangled state to probe this with for that hypothesis test? And that's a much more difficult question to ask. And I don't know the answer to these questions.
Okay, we'll talk offline. Yeah.
Let's talk more about that. Okay, good. So so I give you two examples. This is a third example. This one I will not talk too much about. A colleague of mine, take a look at Dal Wilson's group. His name is Dalziel, D-A-L-Z-I-E-L, Wilson. He is an optomechanics person. So in his lab, he has an array of what he likes to call nano trampoline network. You know what a trampoline is, right? It's a little mechanical membranes. He has a network of them, and he is obsessed with using entanglement to look for dark matter. So basically, you can use entanglement for the same reason that the RF photonic sensor example or the beam deflection example works. You can use, take a squeeze vacuum source, and this is a proof of concept experiment that Jashan's group led, split it on a beam splitter, and this entangled state they use for sensing some correlated signature of vibrational motion across two membranes, and they showed that you can do better than not using squeezing, not using this entangled state. And they are now looking at multiple mode vibrational measurements for very, very tiny force sensing. But again, entanglement helps when you're asking some very specific questions embedded in that spatially correlated force field. Same reason. Okay, so you should take a look. Another paper, another direction I would like to point you out to. I know that some of you are looking at machine learning, quantum machine learning. I think I spoke with somebody or two people who are working on VQAs. In the recent years, my colleague Chuntao Zhuang, he was at University of Arizona. Now he just recently moved to the University of Southern California, USC in LA area. What he's saying that, well, we know that the squeezing passed through a linear optical interferometer, that entangled state is good for certain sensing tasks. He's saying, what if you don't have a very well-defined hypothesis test task? You have an ill-defined task. You're trying to tell apart between different phase configurations. Perhaps you're trying to tell apart between different signals embedded in that microwave field in the RF photonic sensor. How about you can use variational algorithms to train both the state preparation side that generates your entangled probe and also a variational circuit for the linear optical interferometer before your homodyne detector to train the measurement side. And he found that you can tell apart between, say, hypothesis much better compared to just using a classical sensor with a support vector machine at the output of a homodyne detector, compared to what you can do by pushing that support vector machine into the quantum domain to train both the probe state and the receiver side. And this is a very nascent area. I'm sure there's lots and lots of new research and new ideas that are going to come in the space of pushing traditional classical machine learning like algorithms into the quantum domain. By pushing so, you have access to much richer manipulations because you are in the quantum light. You can do things like squeezing, which there is no equivalent of that you could have done after the short noise hits on your classical light. So that, and Chuntao's work is probably one of the best in this area that you can take a look at. Okay, so now I'm officially at my second lecture. So I'm at what? An hour. Okay, good. So this second lecture, I think I should be able to do in an hour because this has much less difficult material than the first one. So my plan, let me take one quick pause. Any questions about, so I'm not going to go back to entanglement assisted sensing anymore towards the end.
Hello. Yeah. So you showed that graph of largest component size versus lambda. So So what does it mean for largest component size to be 1? I didn't get that intuition.
I see. So let's say I have a graph of n nodes. Okay, so I have a square grid, a graph of n nodes, and or let's say n edges. And each edge I put with a probability p, and I don't put with a probability 1 minus p. Okay, so I have a missing edge, missing edge, missing edge, missing edge, and so on. After this, what I do is that so this is a big graph, and let's say it has total number of n edges. Can you tell me on roughly how many edges will be present?
So total edges.
Yeah, the total number of edges is n, and each edge I'm actually placing the edge with probability p.
E by n.
E by n. What is the total number of edges if p equal to 1? It's n. P is the probability between 0 and 1 that I'm placing an edge. So if I count Pn, very good. So Pn is the average, and you know the probability distribution of how many edges will be there? Binomial distribution. Anyway, doesn't matter. So Pn, roughly Pn edges. But what you can do is that now you can go and look at islands of connectivity. Like this is an island that is connected. Maybe another island that is connected, another island that is connected. Find the largest island. Find how many edges are in that island. Let me call that size of the largest connected component. Divide that by n and plot this thing as a function of p. What would you expect at p equal to 0? This number will be 0. What is the value of this at p equal to 1? All the nodes are there. So this thing is n. All the edges are there. So this will be 1, right? What is the behavior in middle as I increase p? What happens is that it could be like this, it could be like that. But when you do you can go and code it up in Python or something. What you will see is that the behavior will look like this. At p equal to 1/2 for a square grid, suddenly you will see that this thing will go from 0, it will start increasing. So over here, when p is say 0.6, and if this number is 0.8, it means that 80% of the edges is part of one large connected component, and all the other islands, their size is not order n. Only this one has an order n size, 80% of the total order. So that's what I meant by the giant connected component. Is that clear?
Yeah, thank you.
Okay, good. There was one more question in the back.
Yeah, so you mentioned about this cluster states or photonic graph states. So if I understand correctly, physically, those translates to just the resultant state, which is caused by a certain set of CZ operations and Bell measurements, right? Is that what physically a graph state means? Or
no, physically a graph state means that if you take a graph, draw any graph you want. Every node of the graph, you place a qubit, initialize it in a plus state, 0 + 1 / √2. And everywhere there is an edge in the graph, between the two qubits at the endpoints of that edge, you do a control Z gate. The end product that you will get is called a graph state. It's a form of a stabilizer state.
okay.
And if you're interested learning more about graph states and what you can do with it for quantum computing, quantum repeaters, quantum sensing, there's a whole host of applications of graph states. So that's why people are interested in them.
Yeah, thank you.
Okay. No, go ahead.
I was just curious. This support vector machine, the quantum assisted support vector machine, if I go from classical parameter space and embed it into some unitary space, the hyperdimensionality, the dimension of the hyperdimensional space I'm going to is much larger typically, right? Because of the 2 to the n. It's a silly question, but that to me sounds like you're actually moving farther away from being able to find the discriminating hyperplane, because you're in a much larger space. The problem is much bigger. And typically people travel in the opposite direction, right? They try to cut down the dimensionality.
Very good point. I don't have a very good answer. One answer I can give you in the context of at least what Chuntao did. He only had Gaussian states. Okay, so with Gaussian state, an n-mode Gaussian state is fully described by a 2n × 2n covariance matrix. So maybe in his case, he was not facing that dimensionality challenge.
Yeah.
But that's a very interesting observation.
Yeah. Thanks. Yeah.
Okay, so let me go to the second part of the lecture, and if there is still time at the end, we'll come back to and do some more questions. So just to remind you of my outline from yesterday, today in this lecture, I'll talk about detection theory. We talked about estimation theory, we'll talk about detection theory, some applications, and the majority of my time I want to focus on an application in passive imaging, telescopes. We'll be dealing with classical light. or microscopes, but we'll be using quantum tools to find better receivers. That will be the focus. So let's go ahead and get started. If you guys are interested, there is a workshop I have been organizing for the last almost now, well, because the COVID, we had a 2-year break, almost 9 years now, on quantum nanophotonics that brings in people with an experience in classical optics, quantum optics, and nanophotonics. And this we had this last year at this Biosphere. It's a beautiful venue outside of Tucson. If you are interested, let me know, take a look at the website. Okay, so this slide we talked about yesterday, so I won't have to belabor the points. The fact that you have a ideal laser pulse, if you feed it into a photon detector, infinite bandwidth, you get a Poisson point process. N is the mean photon number, alpha is the amplitude, and alpha is a complex number. If you detect with an ideal detector, you get a random variable that has a Poisson distribution with mean mod alpha square. We talked about this yesterday. I just wanted to have it still because I'm going to use this. Second thing I talked about was interference. Again, just a reminder, the beam splitter. 2 coherent states meet on a beam splitter, transmissivity eta gives you 2 coherent states at the output given by this formula. So if this is alpha 1 and alpha 2, this is a 50-50 beam splitter, I will get an alpha 1 plus alpha 2 over root 2 and alpha 1 minus alpha 2 over root 2 if the phase is 0. So if I have alpha and minus alpha, I get square root of 2 alpha 1 over here, vacuum over here. This is an interesting example that I showed yesterday, which I did not do anything with. This example of an interference, I have an alpha here, alpha 1 is alpha. Alpha 2 is beta over square root of 1 minus eta. Beta is a complex number. Put it into this formula, the first line. Phi is 0. Square root of eta times alpha 1. Eta is very close to 1. So alpha 1 is alpha. Square root of eta times alpha 1 is alpha, close to alpha. The second term, alpha 2 is beta over square root of 1 minus eta. The square root of 1 minus eta cancels. I get beta here. So this setup, multiple experiments have used it to add 2 complex numbers. It's called nulling, or a displacement operation in quantum optics. You can displace alpha to alpha plus beta using that circuit. Now, if I were to detect after the displacement, I can think about this whole box, the displacement followed by the detection, as a new basis in which I'm measuring alpha. It's a displaced number state basis for those of you who are familiar with quantum optics. But what I have done is change my detection statistics. It's still a Poisson distribution, but it's mean instead of being mod alpha squared, it is mod alpha plus beta squared. But beta is in my hand. I can decide how much to displace and then detect. Why will I care about such a thing? So let's look at some examples. So the first example will be what in the communication theory people call binary phase shift keying. I have 2 coherent states, alpha and minus alpha. I want to tell apart between them. If you do photon counting between these two, will you be able to tell apart between these 2 options? No, because both of them will generate the same Poisson point process, the same rate. You will not be able to tell them apart. Okay, so this doesn't work. Photon click patterns is the same statistics. But we learned about homodyne detection yesterday, right? So homodyne detection, you will get a Gaussian random variable with a mean of alpha or minus alpha with a variance of 1/4. And now you can put a threshold in between and you can get a probability of error of telling them apart. It is this Gaussian error function, which is the integration of the tail of this Gaussian square root of 2n. So homodyne detection is how people tell apart between BPSK signals. This is what the performance of a local oscillator, short noise limited ideal homodyne detection will get you that error probability. Is that the optimal receiver? Like, does physics allow us to have a receiver that will go below that probability of error? Because this is the only receiver that we know how to build to tell apart between 2 coherent states, alpha and minus alpha. Okay, so let's look at a very simple example first. What if I applied this displacement by beta to move alpha to 2 alpha and minus alpha to 0? Is that clear? So I have chosen beta equal to alpha. So I start with plus and minus alpha and I move it to plus alpha plus beta and minus alpha plus beta. And beta is alpha means this will be 0. Now will you be able to tell apart between them by photon detection? You will be, because you have taken away the photons from one of them and the other one has a lot of photons. Okay, so if you were to work out the probability of error, let's say that each hypothesis is equally likely. The probability of error is the probability that hypothesis 1 is true, which is the minus alpha hypothesis, times the probability you will make an error. When will you make an error if this hypothesis is true? Well, when k equal to 0. And that will happen with probability e to the minus 2 alpha squared, because this hypothesis is my probability hypothesis 1, the alpha hypothesis. So the only way you can make an error is if this guy doesn't give you a click. What about the other term? If this hypothesis is true, will you ever make an error? You will never make an error because this will not give you a click and you will guess that is the hypothesis. So you get a probability of error which is 1/2 times e to the minus 4n. Okay, so hold on to that thought. So I've given you a different receiver where I have suddenly turned that direct detection into a useful thing for telling apart between alpha and minus alpha by simply doing the displacement before. So that displacement was a change of basis of measurement that was able to extract information in the photon in a way that was not possible by that detector that I had. So this pre-detection transformation is a theme that is going to run through my entire lecture today. So this is just one the simplest example that I wanted to put out. Okay, so let's keep building upon this. What about I did not stop at beta equal to alpha, I displaced it further out. What will happen? If you look at these two terms, this term is no longer 0 because now beta will have some probability of getting 0 clicks when I'll make an error. So it's 1 minus the zero probability of 0 clicks for a coherent state beta, which we know is the first term of the Poisson distribution, e to the minus beta squared. And the probability of getting 0 clicks for a 2 alpha plus beta coherent state, what is the Poisson distribution's first term? E to the minus the square of the mean, 2 alpha plus beta squared. If you optimize this probability of error over the choice of beta, you will find that the optimal beta is not alpha. It's very counterintuitive that Masahiro Takioka and Masahide Sasaki, they found in this 2008 paper. And the thing is that this error term increases, but this one decreases even more so. So it compensates for it and there's an optimum beta. I don't want to write the formula. You can now plot everything. Take a look at it carefully. This pink one is the homodyne detections error probability as a function of n. The red one is the Kennedy receiver, the one where I chose beta equal to alpha. The blue one is the optimized beta. So I've given you 3 receivers, but who tells me that any one of those 3 receivers is optimal? I've no theory. I'm intuitively designing all these receivers from my head just by looking at these states. What is the best possible error probability that the laws of quantum mechanics allows? And I'll tell you how to derive that, but this is given by this black line and that crazy looking formula here. And Sam Dolinar, he is at Jet Propulsion Laboratory now, but in his PhD thesis in 1973, you're welcome to take a look at that thesis, beautiful 200-page dissertation just on finding a receiver design that achieves that black line. And all he uses is linear optics, meaning beam splitters and a local oscillator coherent state and photon detection, but he uses feedback. So he applies the displacement just like I talked about, before you detect, but after every detection events, he flip-flops between applying 1 of 2 time-varying displacements across the whole pulse disk duration. And finding these formulas for the schedule of these displacements is the product of his PhD thesis. It's a beautiful result. And unfortunately, this idea of using displacement, classical coherent state light, photon detection, and feedback does not work to get you to the quantum limited performance for even 3 coherent states. For 2 coherent states, any 2 coherent states, Dolinar receiver works. Okay. So first of all, let's take a break and see how do we even calculate that formula. I mean, this is the power of quantum estimation theory, quantum detection theory. Even without anybody telling you what the optimal structured receiver looks like, you can just do a few lines of math and say, this is the best possible thing you can ever do. Laws of physics tells you that. Then you can work hard trying to see if you can bridge the gap between that performance. Okay, so the next slide, stuck again. No, so this is something you all know, so I don't have to belabor these points, but I still want to put my notation out there. Pure state of a quantum system of a bosonic mode, I'm going to write using a psi. A measurement, a projective measurement is described by a complete orthonormal basis in which psi lives, okay, WKs. The probability of the kth outcome is the squared magnitude of the inner product between the kth measurement vector and the state. And let's say if you have a binary hypothesis test, I have two states, psi1 and psi2. If I give you 2 states with a real valued inner product, you can put them on a plane of a paper, right? 2 unit vectors with a scalar inner product, I can put it on a plane. And the most general measurement I can use to tell them apart is just, two vectors that are at 90 degrees to each other. So the only thing I need to optimize to find the optimal error probability is how these 2 90 degrees vectors, the measurement vectors, are oriented with respect to the state vectors. So I have to just optimize this phi. So you can write down the probability of error if I use this measurement vector to tell apart between these two states. Let's look at this carefully. Probability of error is probability that hypothesis 1 is true, psi 1 is true, times the probability that you choose hypothesis 2 given hypothesis 1 is true. What is this probability of error? 2 given 1, it is the inner product between psi 1 and W2 magnitude squared, right? So you can write down this thing and I'll let you do the math, optimize for phi. You will find this formula for the minimum probability of error when P is the prior probability of alpha. So Dolinar knew to calculate this, in 2 lines, but finding the receiver, took him 5 years. This is the power of quantum estimation, quantum detection theory. When P is 1/2, this formula reduces to just this 4P, 1 minus P goes away. It's just 1 minus sigma squared. This is called the Hellstrom limit, by the way, in the literature. And I just showed you the derivation of the Hellstrom limit for 2 pure states. All right, so psi 1 and psi 2, if they were states in a 2-dimensional vector space, you can also think them as a qubit. We talked about quantum description of a laser light pulse yesterday. I still had this slide just to remind you of the notation. We talked about Fock state of a mode n being a state that has exactly n number of photons. They will arrive at random times. Every time you do an experiment, there'll be exactly n number of photons. But now in the previous slide, you have seen the only way 2 pure states can have a probability of error of 0 is if those 2 states are orthogonal, right? If you look at this formula, there is only way I can have P in me equal to 0 is if if the inner product between these 2 states is 0. If I put 0, 1 minus 1 is 0. So if I give you 2 Fock states, 1 and 2, you know how to get a probability of error of 0. Just do photon detection on it, right? You will get 1 photon, 2 photons. So 2 Fock states have to be orthogonal to each other. And Fock states have fixed number of photons. So if I go from 0 to infinity, they span all the photons, all the energy. So intuitively, you see why Fock states form a complete orthonormal basis for any state of a single bosonic mode. So you can write any quantum state as a superposition of Fock states. A coherent state has this form. This is a square root of a Poisson distribution. And now you can calculate the inner product between 2 coherent states. So if I give you any 2 coherent states, alpha and beta, their inner product is never 0. So meaning 2 states of laser light, you cannot ever distinguish with probability of error of 0, especially when they are small. Okay, so now I can write down photon detection as a measurement in the Fock basis. So your probability of getting n clicks is given by the Poisson distribution, which you are not familiar with, but this is the quantum notation of everything. And inner product between the 2 BPSK coherent states, the alpha and minus alpha, is you take this formula and substitute beta equal to minus alpha, you'll get this formula, e to the minus 2n. Plug it into that formula for the Hellstrom bound. It is 1/2, 1 minus sigma squared. The sigma squared is just e to the minus 2n squared, e to the minus 4n. So that was the derivation of the minimum probability of error. But I haven't shown you how to derive the receiver. I will not have time to show you the design of the receiver. But this is how you derive the Hellstrom limit. But now that you know how to calculate the Hellstrom limit for telling apart between 2 states, you don't need to stop at 2 states. You just keep going, 3 states, 4 states, the same story, right? But even though I have no idea, I cannot tell you even right now, how would you design an optimal receiver to tell apart between 3 coherent states, 3 states of laser light. So let's look at what people did for multiple states. And this was work done by Horace Ewan, Bob Kennedy, who was Dolinar's supervisor, and Lax. So UN, Kennedy, and Lax, YKL limit, as some people call it. Well, nowadays people call it the Hellstrom limit, but it's actually those 3 people who wrote the first paper on this. Hellstrom cleaned it up, and he did a lot of very interesting work, follow-on work. Okay, so you now have M states, some state psi, and you have their relative inner products. Now, let's take, I have 3 states. Instead of 2, I have 3. I know this inner product, that inner product, this inner product. I want to design a measurement. So I have now 3 orthogonal vectors. I want to orient these 3 vectors, W1, W2, and W3 with respect to my states. So what you actually want to find is the inner product between my Wi's and my psi i's. If you find that, you can find the error probability. So this Wi psi j, these xij is what I want to find. Orient the measurement vectors with respect to the state vectors. For what? Such that the minimum probability of error, which is 1 minus the average success probability, is minimized. Why is this a success probability? Because it's the average probability that my ith hypothesis was true times, given that the ith state was received, psi I was received, that I chose it to be Wi. So Wi psi I magnitude squared is xii. magnitude squared. So this is the probability of error. And the UN Canadian lags, they proved that all you have to do is to solve this set of nonlinear simultaneous equations for the xij's given these overlap between the state vectors, and you can put it in here and you will get the minimum probability of error. Okay, so these are called the YKL equations. Well, you can solve it now for something like this, 0, alpha, and minus alpha. For communication theorists, this is called the binary phase shifting return to zero modulation constellation, the name for it. I don't know how to design an optimal receiver for it, but I can solve the YKL equations. I have the pairwise inner products between them from the formula. Traditionally, you would use homodyne detection to tell them apart, right? You will get a Gaussian distribution with mean of 0 alpha or minus alpha with a variance of 1/4. But if you calculate the homodyne detection's error probability as a function of n, goes as e to the minus n over 2. Whereas if you solve the BiKL conditions, you'll get a probability of error that scales as e to the minus n. So there's a huge improvement. But the optimal receiver this time, you cannot design that optimal receiver using coherent states, beam splitters, and photon detection, the 3 physics tools that I have covered in my lectures. You will need to bring in things like squeezing to describe the photo detection statistics of which properly you are going to need to invoke quantum optics. So Dolinar got lucky with 2 states. He was able to design a receiver that attains the quantum limit, but by using tools that can be properly described still using the semi-classical theory of photo detection. But for the general case, you're going to need quantum operations. But then if you're just interested in achieving the correct error exponent, but not the exact Hellstrom limit, you can achieve it with this Kennedy-like receiver that uses this displacement and photon detection. Okay, so this is a application I wanted to show you of all the things that you have read now, because with everything that you have seen in this lecture, you can derive everything in this 2021 Nature quantum information paper. This my former postdoc, Kaushik Sheshadrisan, Narayanan Rangaswamy, he's now a faculty at University of Arizona. He was a postdoc 2 years back. He became a faculty member, very, very accomplished error correction theorist. And they looked at this problem of telling apart between these 8 code words. What is a code word? This is 5 pulses, 5 time bins, alpha or minus alpha for each time bin. How many options are there? There are 32 possible sequences, right? 2 to the 5. But let's say of those 32 possible sequences, you only have 8 sequences. I have guaranteed you that I will only give you those 8, one of 8 code words. And your job is to find out which one I have given you. Minimize the probability of error. What will you do? Well, you solve the YKL conditions. You will find the relative inner products. Now, alpha minus alpha inner product is, let's say, X. What is the inner product between psi 7 and psi 8? You count how many places they differ, like 1 place and 2 places. It will be X squared. So the general inner product between the ith and the jth code word is X raised to the Hamming distance between the 2 code words. This is the number of places in which they differ. So Kaushik went ahead and solved those crazy simultaneous equations and found this, pink line. Probability of error as a function of mod alpha squared on this axis. But the rest of the paper was about finding an actual receiver that achieves it. And that's something I will not be able to go into today. There's a technique called belief propagation in classical decoding theory. But we know that if I detect symbol by symbol each of the 5 coherent states, I will not be able to get to the quantum limit. So we had to figure out a clever way, again, similar in spirit to this machine learning thing. We pushed belief propagation into the optical domain and was able to now use quantum belief propagation to actually achieve the Hellstrom limit for this problem, which was not, which in this case cannot be achieved classically. So that was the whole point of this story. Take a look at this paper. If you're interested in this, I can tell you more. Okay, so let me in the next half hour talk about the last topic I want to spend time today is on quantum limits of passive imaging. But I can take a little pause here and take any questions about discrimination between laser light pulses, if there is any. Okay, so you should be ready for the last topic then. Okay, one question.
A few slides you showed the inner product for the coherent states, right? So you wrote that in the Fock basis. And you said that you can't get a orthonormal basis for that because you wrote that in the Fock basis. But if you are limiting, I mean, suppose you have only 2 coherent states and you want to detect something in that, you can find an orthonormal basis for that, right? I mean, if you have only 2 coherent states, if your system is
if I only have 2 coherent states,
yeah. Like you showed one with 0, alpha and minus alpha, then you can find a orthonormal basis for that and do your measurement in that basis, right?
So the inner product between two vectors, they don't depend upon the basis in which I express them, right? So the inner product between two coherent states has nothing to do with the fog basis.
You can still find an orthonormal basis, right?
Exactly, and that is what the YKL basis did.
Okay.
So very good point. So this alpha, 0 and minus alpha, these three states, they form a isosceles geometry, right? So alpha, 0 and minus alpha. Isosceles geometry meaning what? The distance between two states is the same. The distance between 2 and 3 is different. It's
right.
like two states like this, and the third state is over here.
Got it. Yeah.
And the optimal measurement is an orientation of three vectors at 90 degrees to each other, which minimizes the average error probability. That's exactly what the YKL condition does.
Got it, sir. Yeah, thanks.
Good. Okay, any more questions? Okay, let's talk about passive imaging. So this is a topic that I think you will find very interesting because there has been a lot of recent talk and things that you have heard about. Have you guys heard about the James Webb Space Telescope, the JWST? This huge telescope that NASA launched here. So I'm sure you have seen that. And why do they like to build big telescopes? Because they can resolve smaller things. The bigger the telescope is, the smaller the features you can resolve, deeper in the universe you can look at. Same idea, build a bigger objective. In a microscope, you can resolve tinier things. So we will look at what does quantum mechanics say in terms of the fundamental limits of imaging. So let's look at this very canonical problem of resolution. So I have two stars with angular separation theta. This is my entrance pupil of my imaging system. It could be think of as a d as the diameter of the primary mirror of your telescope. What happens is that if I had a single star, I get a blob of light on my camera, on my focal plane, whose width is roughly lambda by d, where lambda is the wavelength of the light and d is the diameter of the pupil. So see that if d is big, what will happen? That thing will become narrow, lambda by d. And that's why you can resolve stars very well. So now see, if there are two stars, I get this blob of light, and there the angular separation, if theta, if this is much smaller than lambda by d, then I will not be able to tell them apart. That's the conventional wisdom. What you do conventionally in a telescope, you have a CCD array or some sort of a direct detection device. Each of these pixels will generate a Poisson random variable, and then you write a maximum likelihood estimator, which you know now, and write down the variance of the estimator, where you also know the variance of the estimator goes as the one over the Fisher information. You can go ahead calculate the Fisher information from the Poisson statistics. By the way, all these calculations that I'm talking about, you have all the tools from yesterday's lecture to go ahead and derive. In fact, you can derive this formula for the Fisher information for an ideal focal plane array for telling apart between 2 point sources. But look at this formula. Fisher information I'm plotting normalized to sigma square, where sigma is this thing, divided by n, where n is the total number of photons I have integrated, total mean photon number over the integration time. This axis is the separation between the 2 point sources in units of lambda by d. So notice something, that when this quantity, when theta becomes smaller than lambda by d, this is called the sub-Rayleigh regime or sub-diffraction regime. Your Fisher information plummets to zero, towards zero. And this is what the math of Fisher information is telling you quantitatively, that how does the decay rate of your variance as you're increasing the mean photon number diminishes as your angular separation is shrinking below the diffraction limit. Okay, and by the way, if you look at here, say theta 5 sigma, your j of theta is roughly n by 4 sigma square. So this line is n by 4 sigma square. And since I'm multiplying by sigma square by n, that's why it is 1 by 4 over here, okay? So if my theta is say 0.5 instead of 5, my Fisher information is 0.025 instead of 0.25. What does it mean physically? I'll need to integrate 10 times as long to get the same variance of the estimator as compared to if my angular separation was 5 sigma.
Sorry, just a clarification. Yeah. This is the classical Fisher information for
classical Fisher information.
For that histogram measurement.
For that direct ideal photon detection array. So we are saying that if you could build the best possible focal plane array that the laws of physics allows you, infinitesimally tiny detectors, no 100% fill factor, unity detection efficiency, zero dark click probability, no after pulsing, perfect detector. That is the Fisher information for it. But that leads to the question, what is the quantum Fisher information? So before we do that, let's see what that histogram will look like. When your separation is above sigma, you will actually see two peaks in your click pattern in here. But when you're below sigma, you will not visually see two peaks. You will, I mean, the maximum likelihood estimator will give you an estimate, but you will see one peak. This was the intuition why Rayleigh, I mean, 100 years ago, he wrote this limit. And he was perfectly right. If you use the camera, this is the limit. You can't tell them apart if the two things overlap. But what is the quantum Fisher information? You now can calculate k of theta from my slide yesterday. And Mankey-Sang, who did this calculation first, he found a really, really surprising result that sort of blew away some astronomers. And initially, I was in some conferences where some astronomers, they basically said that I don't believe this result. So, but let's leave it at that. But they found, so Mankey's result was that this k of theta is a straight line. It doesn't fall. Okay, so that means that, I mean, we heard that there are quantum Fisher information for a single parameter is achievable. There must be a receiver that achieves that performance. So what is that receiver? So Mankey also found that receiver. It's not the SLT measurement. It's a different measurement. And his measurement is the following. You build a mode sorter. So what is a mode? You take an electric field and you can express any field in some orthonormal basis. So let's say I choose to represent my field in, let's say, the Hermite-Gauss basis. Right? I can express in any orthogonal basis. So this is the basis, meaning what? If I take phi nm star x comma y, phi nm phi kl x comma y, dx dy, this thing equal to delta nk delta ml for all mn. A mode sorter is a device that will separate out each of the components of that basis. And so on. So this is known as, so if your modes in which you are representing a field are orthogonal, there must exist a device that sorts them. So Mankey showed that if you had a mode sorter that sorts the Hermite-Gauss model basis, you achieve that k of theta. Your j of theta equals to the k of theta. He called it a spatial mode demultiplexer or a SPADE. What is the intuition behind this? So in his setting, he had assumed that you exactly knew the center of the two stars. So that's why he got the exact straight line. And when you sort the modes, when they bring the stars closer and closer together, the center mode, the phi 00 mode, that has the most of the photons in it. But those photons are the least informative photons. Because if I'm looking at a tiny object far away, I will always see a big blob in the middle. And that blob mode, that center TSF mode, is the least informative mode. So if I can take that mode away, and I'm able to do Poisson short noise limited detection on the higher order modes, I suddenly get a lot of information. So that was an intuitive way in which he designed the receiver. But turns out it achieves the quantum Fisher information. Okay, so then he found that not only so, even if I sorted just the first mode, the zero order mode, with the rest of the light, its classical Fisher information for a binary SPADE, B SPADE, still achieves the quantum limit when your angular separation is very sub-Rayleigh. This was even more exciting because instead of building a big gigapixel array, you just need to design a very, very good quality mode sorter and just two detectors. But then suddenly after this, there was some criticism where people said that, well, all of these results, they assume that I know exactly the centroid of the two stars. And you are never going to know that. If you're looking at a binary star constellation, you will not know that. So, well, we decided, this was Michael's first PhD project when he started with me, my group. He said, well, let's say I don't know the angular separation. It was a toy problem. So said, you don't know phi. It's I think Sai mentioned this. It's called the nuisance parameter. So phi is a nuisance parameter. You don't care about phi, but you have to estimate it nevertheless in order to estimate theta, which is what you care about, the angular separation between them. So Michael said, I'm going to use a normal focal plane array for some fraction of the integration time, just to get that nuisance parameter, just to know where to point my mode sorter, that middle, the center of the blob, phi. Then for the remaining part of the integration time, he takes a binary mode sorter, points it to that imperfect estimate of phi, and then he uses it for the rest of the integration time. And there's an algorithm by which he chooses how that dynamical switching happens from the stage 1 to stage 2. And now he does a proper Monte Carlo, no Fisher information. Like proper Monte Carlo, the mean squared error as a function of theta. Over the entire subreal regime, you get a 10 to 100x improvement. Meaning this is now a real thing. This is something you could actually build, right? So you can get the same mean squared error, but with 100-fold fewer photons. So this result really started a line of work funded by an agency that you may have heard of called DARPA in my group back in 2017. Caused a lot of excitement that Manke's result was not just a fluke, that he did not assume that center, although he's the one who really started this whole line of research. But what was the intuition behind all this? So the intuition we derived in this paper, but by the way, this paper, to understand this, you need zero quantum mechanics. It's a completely classical optics paper. So feel free to read it if you want to understand this whole theory. Point is that normally in astronomy or biology, fluorescence microscopy, if you have 2 stars, you will estimate x1 and x2, the 2 positions, right? But estimating x1 and x2 is same as estimating x1 plus x2 and x1 minus x2. We know this from simultaneous equations. x1 plus x2 is the centroid by 2. x2 minus x1 is the separation. x1 plus x2 is a much easier thing to estimate than x1, x2 minus x1. So why should you give the same resources to the 2 things, right? You should provide direct detection, which is very good at estimating x1 plus x2, but give it very little time and focus your energy on estimating x2 minus x1, but you do need that x1 plus x2 estimate in order to point your mode sorter. So that was the philosophical, the intuitive part for why this works. But with modal imaging, one important thing is that we don't quite see the stars. Like Michael's Monte Carlo generated an estimate of the stars, but when I was trying to explain this to an astronomer friend of mine, and now we are actually working together, it took me a long time to see. In astronomy, they see an image that comes out of the telescope. In this case, it's like you have this magic optical thing and then a computer that generates the image of 2 stars. It's an indirect imaging. So there is no image that it creates. You're creating the image through this receiver. Anyway, so then we said, well, over the last several years, we've cycled through 3 PhD students, 1 postdoc, and we started looking at more and more complicated versions of this problem. And we said, well, the most general problem we wanted to look at is, this thing is a angular field of view in Rayleigh units, so minus 0.4 lambda by d to 0.4 lambda by d. We threw in randomly placed point emitters. So the black dots are stars. I didn't give any information about where they are. The only information that your receiver has is that you have some unknown number of point emitters of equal brightness, and there is nothing else in your background. So in the astronomer's language, you will say there is no clutter. There is nothing else in your scene. You just have some stars. And your job is to localize them. But now I have an unknown number of stars, and each has 2 parameters, xi and yi, their position, that you want to estimate. So this is something I will not go into. Do you remember the personic bound I talked about? The very beginning, the first slide of my lecture yesterday. This is the Bayesian quantum bound that achieves the minimum mean squared error for a given prior p of x, then rho of x is the state that carries that parameter. That was the workhorse behind the work we did in this paper. And here we said that in every little time segment, your receiver tries to figure out what is the right linear combination of these xi's and yi's that it should focus on. And when I said right, we find the highest eigenvalue eigenvector of an SLD-like matrix that I talked about in the Bayesian context that tells you the right direction in that parameter space for you to focus on. We find the personic projector for that measurement, turn it into a modal basis, you make a measurement, get your photon clicks, use that to update the posterior probability on all the parameters, recompute which is the next best parameter for you to estimate, and you keep going. And when you do that, in this case, an ideal direct detection imaging, it is generating estimates of 2 stars. The circle's width is the brightness estimate. It thinks there are 2 brighter stars in a random place, whereas our modal imaging can localize them. See, our modal imaging thinks there are 4 stars. But I'm actually happy with this estimate because these 2 estimates are pretty much on top of that actual star location. And this was another example. We are running a simulation, 30,000 photons to 90,000 photons. Just there's a video that I would not upload, so be content with this figure 3 snapshots. You start out like this. These are our estimates from the adaptive modal imaging detector. See, even at 90,000 photons, a conventional telescope thinks there is 1 bright star at the centroid of the 3-point sources, but our algorithm can find them. So this is from just a few months ago, and we are now about to launch into the next transition phase. So DARPA and is now going to work with NASA to do an experimental demonstration of this with an actual instrument and build a mode sorter and actually show that this thing works. So this is now very, very exciting. So
can I just ask, 90,000 photons is what kind of time are we looking? If I just point myself in the night sky, what is this?
That's a good question. This really depends upon the wavelength. And the main thing is that all of this that I'm doing, this is quasi-monochromatic. Nothing is quasi-monochromatic in the real world. So something I'm not telling you a part of the story is that you are going to need a bank of a spectral filter bank and a few mode sorters, not too many, 3 to 4 mode sorters at different wavelengths. But what happens, what Michael's PhD thesis showed, I mean, this is the part that we haven't published yet, that the classical quantum gap, so to say, it increases when you go to broadband radiations, but there's more photons to work with. But your photon rate of arrival is also going to go up. So it's hard for me to put a number here. So this is just you can think of this as a parametric problem. But we have some actual numbers that we have worked out. But it will basically boil down to that if I have the JWST telescope, if I enable this modal receiver, suddenly you'll be able to look further, deeper into the universe, because you will have more resolution power. But it will not create an image. It will just come out of this modal imaging receiver. So that's why NASA is very interested. And if this works, they might incorporate this into what is called the Habitable World Telescope, which is the next big telescope program they're about to launch and announced it yet. Okay, so I kept talking about astronomy, but something that Kasturi and I have been talking about in the last several months now. You're going to see, I believe in your talk, are you going to show the pictures of those? No, you're not going to show the pictures of NVs. So when you take nitrogen vacancy or silicon vacancy color centers in a bulk sample, if you look it under a into another confocal microscope, you see a bunch of dots, just similar to those black dots I was showing, except that it's now full of emitters. And the separation between those emitters is highly, highly sub-Rayleigh, like 10th or 20th of a Rayleigh. And we need to find where those emitters are. And this modal imaging camera will be able to find them better. Not only that, if those emitters are being used to sense a magnetic field, a local magnetic field applies a small detuning to the level structure that I showed that affects the photoluminescence spectrum of your emission. So if you are able to not just resolve where the point sources are, but also their brightness, you can use this as a super resolution magnetic field imaging system. It's something that we are working on right now. Okay. And there are applications in fluorescence microscopy and astronomical imaging, also in telling apart between different objects for space situational awareness, and lots of applications of this technology. Okay, so how do you build a mode sorter? How do you build this device that I wrote here? Many different methods. The method we have chosen to use is called multiplane light conversion. So I'll skip one slide and show you, this is a better slide here. So if I have an object, a field, that I let pass through a Fourier transform between here and here, followed by a spatial light modulator, which applies a spatial phase to the field, e to the I theta of x comma y multiplied with the field. Another Fourier transform, another phase, another Fourier transform, another phase. If you do that enough number of times, you can sort absolutely any orthogonal modal basis. This thing is called a multiplane light conversion. It's a kind of way to build mode sorter. So Michael, my former student, and Ita is a PhD student, they build this mode sorter in my lab. It's a toy proof of concept experiment, but it is fully programmable. It is very lossy right now, but it has a very, very good crosstalk. So here, this example, they coded up these 4 orthogonal modes. So this yellow region is 0 phase, purple region is pi phase. So these 4 are orthogonal 4 phase patterns. And we have designed the SLM phases so that if this is presented to the mode sorter, you will get a blob of light here. If this is presented, you will get a light spot here on the camera, and so forth. This is theory, simulation, with these 3 are the phase patterns, and this is experiment. This is a crosstalk matrix, and we get less than 1% of crosstalk. And even with this data, when this is very raw and published results still, that we can get a factor of 10 or so improvement in the RMSE for that 2-point source problem. We are still cleaning up the data and see what we will get. Okay, so now what about if you have multiple apertures, not just one aperture, if you have a long baseline system or on a segmented telescope. In a segmented telescope is a big telescope with like 3 mirrors or 4 mirrors. Now, if I have two apertures like this, I can think of the two apertures as one compound aperture, which has a aperture transmission function, which is a rect followed by nothing and another rect. And take the Fourier transform, and that will be my new point spread function. So we can apply all of our theory that we developed to this new aperture system. And now this is the quantum Fisher information for estimating the separation between two point sources. So this is the single aperture part that we had already seen. And now there is a contribution of the baseline that comes in. Baseline means the distance between the two. So the R is the ratio between the distance and the diameter. So this is a huge contribution to the QFI. And in this paper, we show how to actually achieve this QFI by bringing light together by spatial mode demultiplexer at each telescope. You bring in light fiber coupled from the first few modes and a fiber optical interferometer in one place. So that's how you can achieve this QFI. Now, what if you are in a scenario, the telescopes are very far apart. You cannot bring the light to one place. Then what would you do? You can still achieve that quantum limit. But now you are going to need to take the light at each telescope, and after the spatial mode demultiplexer, store those photons in a bank of secular center quantum memories. And use pre-distributed entanglement among those telescope locations. We may be supplied by the future quantum internet, and do local quantum measurements, and you can achieve that same quantum limit. And this is something that we are still writing up in this paper, which hopefully should be out in the archive in the next month or so, if Isaac is quick in writing this thing up. So anyway, so I will skip this thing, and this is just a general picture of what he has drawn. The idea behind this entanglement assisted sensing is the following. These are my spades, spatial mode demultiplexer, sorting K modes at each telescope. If I just imagine in my head that all those modes are available to me in one place, we know how to calculate this big linear optical interferometer detection and feedback into this interferometer. That's what the mode sorter is, right? But these modes are not at the same place. Like these two modes are not at the same place. The orange ones are where one mode is here, one mode maybe is 1,000 miles away. So if only I know how to do a 50-50 two-mode beam splitter in a distributed fashion using entanglement, I can compile absolutely any circuit involving an N-port interferometer into a distributed logic. And that's the crux of this paper. All right. So the last part of my talk, I'm going to talk about hypotheses. By the way, that's a Gila monster. Have you guys seen this or heard about it? No. It's, in the state of Arizona, there are a couple of things that are protected by the state. One is this saguaro cactus that I showed you some pictures. If you have a saguaro cactus at your home, if you want to cut it off, you have to take the state's permission, and you have to actually pay to implant it somewhere else in the jungle. So you cannot just, otherwise it's a punishable crime. And Gila monster is another one of those animals that is protected by the state. It's a very, very interesting, unusual flora and fauna in the state of Arizona. All right, so we have talked about detection, we have talked about estimation. Now I'll talk about hypothesis tests when you have multiple copies of one of two states. N copies of rho 1 versus n copies of rho 2. You want to design a measurement that minimizes the probability of error. Classical detection theory, you will pick a measurement. If you pick a measurement, you will get n samples of either this distribution or that distribution. Right? We know how to calculate a distribution from the state and the measurement. We talked about it yesterday. So for that, there is something called the Chernoff exponent. You can write the probability of error as e to the minus n times this Chernoff exponent. The Chernoff exponent is given by that formula. If I don't design a measurement, if I don't pre-select a measurement, and I ask, what is the best quantum measurement I could use on these n copies of either rho 1 or rho 2 that minimizes the probability of error, you can write the probability of error as e to the minus n xi q, which xi q is a quantum Chernoff exponent, which is given by that formula. Now, just like any other quantum bound, I've talked about the Hellstrom bound, the Kramer-Rao bound, now you've heard about the YKL bound, you're talking about the Chernoff bound, same story again. Xi q is going to be larger than xi c for any measurement choice. So this is the power of quantum estimation theory. It automatically optimizes over all measurement choice to get you the best possible performance where the definition of best has to be defined. In this case, it's the minimum probability of error. Okay, so in general, you are going to need a joint detection receiver over all n copies to achieve the Chernoff exponent. Whether or not you can achieve this with just a copy by copy measurement of each state is an unknown problem that we were discussing today. It's still an open problem. Okay, so in this PRL from last year, we looked at using the quantum Chernoff exponent for a fun problem. So this problem was really motivated by No, you have take your phone camera, it's a 3mm camera, and let's say you want to use it to read some barcode or a QR code stamped, say 1 kilometer away. Okay. And you have a focal plane array on which you are just seeing a blob of light because it is so sub-Rayleigh. What is the quantum limit of telling apart between these barcodes? So if you write down the probability of error, it comes out as e to the minus xi n, where n is the total photons you integrated. And Michael and I showed that this xi goes as order gamma squared for the best receiver, where gamma is the length of the object, angular length in lambda by d units. Whereas if I use an ideal focal plane array, this goes as gamma to the 4. So it's a huge separation. And which could mean that you can resolve 10 to 100 times better compared to a traditional receiver. The same concept, I'll not go into details, was also used to look at discriminating targets, on and off targets, in a series of papers that started by this paper that we did in 2008 and some receivers for quantum radars, quantum illumination. This whole line of research, we found that if you are in this funny regime of low transmitter brightness, high thermal noise, and a lot of loss in the transmission, that an entanglement-based quantum radar, where you send 1/2 of a 2-mode squeeze vacuum prepared using a spontaneous parametric down conversion to interrogate a target, you can get a factor of 4 improvement in the error probability exponent, meaning that xi q that you saw is factor of 4 higher than xi c. And we found a receiver that gets halfway there in this 2009 paper, and then I didn't cite the Chuntao's paper from 2017 that he found the receiver that gets to the full factor of 4 improvement. But it's just a factor of 4 improvement in this weird regime that probably nobody will care about. So we did not pursue this line of research too much after this. And then, but recently we looked at a distributed quantum radar using pre-shared entanglement, and under some Bayesian analysis, we found that you can get more enhancement than that 6 dB case. Welcome to look at this paper. It's now published. We did it with Chuntao Zhuang. All right, so the last, I'll take a couple of minutes to tell you broadly about a few other things in my research group. If you're interested, definitely feel free to contact me. You already heard about the spin-spin entanglement generation, looking at how you generate entanglement between quantum memories mediated by photons, generating photon-photon entangled sources and loading them onto quantum memories, let's say for satellite-based entanglement distribution. I talked to you about this decoherence study. It's an open quantum system analysis to understand decoherence mechanisms. Using both photonic cluster states as well as quantum memories for fault-tolerant quantum repeaters for long-distance entanglement distribution. We are looking at entanglement-assisted sensing, which I talked about, but in the context of when the entanglement is itself distributed by a network using probabilistic operations. How should the network be distributing entanglement to a set of sensors that are not located in the same place that maximizes the QFI for some sensing task? Then if the network is allowed to make multi-qubit measurements at every site, not just Bell measurements, then you can be in a regime where you could generate entanglement much more efficiently across the network using percolation theory ideas. We are building a non-deterministic linear amplifier using what is called a quantum scissor that again uses SPDC sources, linear optics, and photon detection to build continuous variable quantum repeaters. In theory, we are looking at entanglement across by partitions of noisy many-qubit entangled states. This is a very interesting topic. Sai and I just had a little discussion about this, collaborating with my colleague Kanu Sinha. She's now at ASU, my student Prajit. There's some very interesting collective effects that happen due to non-Markovian physics when 2 atoms, 2 color centers interact with a waveguide. And we are looking to see if you can generate metrologically interesting states using this kind of a super radiance phenomenon. My first year PhD student, Mushkan, she is looking at using a Gaussian boson sampler to solve NP-complete graph classification problem potentially faster than a classical computer, even though they will both scale exponentially, you can get a constant factor like improvement by using a Gaussian boson sampler to encode a graph and then looking at the output and then using a support vector machine. I talked about how you can have a joint measurement achieves a better communications performance. Remember that example of 8 code words with 5 pulses. We are building a receiver that I had proposed in this 2011 paper with my colleague Linran Fan and my student Jack in the experiment. to show super additive communication capacity, meaning higher performance when your receiver can act on multiple symbols of the code word at the same time. My student Ashlesha, she's looking at all photonic quantum repeaters using photonic cluster states that are generated using atomic memories. And then finally, I talked about the super resolution works. I'll not go into the details of that. You already heard about beam deflection measurements, and this is now work in progress with experimental research along with my colleague Dal Wilson at the University of Arizona. And then if you have pre-shared entanglement among two locations, you can also use it to enhance your classical communications data rate, especially if you are in this regime of high noise and low transmitter brightness. The same reason why quantum illumination gave you the advantage in that funny regime. If you are in say, a radio frequency regime where you have a high thermal noise, and for some reason you want to transmit very weakly, maybe you're whispering into the noise, you can get a factor of 10, 20 enhancement in the classical communications rate. And we have some done very interesting work in this area. My student Ali Cox has been doing some work. Entanglement assisted photonic sensors has many applications. Quantum enhanced receivers for laser comm. We are building a squeeze light source for, again, mechanical deflection measurements. And this final project, for some of you told me you're working on measurement-based quantum computing. Might find this paper interesting. We're still writing the long version of the paper. The student Ashlesha, she came up with, have you played the game of Tetris? It's a quantum tangram puzzle where you have these little puzzle blocks that you have to put together. So she has found this version of Tetris that she actually has had class 10 students play, because you don't need any quantum mechanics to explain her rules of the game. But if you get better and better at playing her game of Tetris, you will unknowingly get better and better at mapping a quantum circuit more resource efficiently into a measurement-based model of quantum computing, which is a hard problem. It's an open problem. So this is, I think, her hidden interest is to outsource the problem to kids who don't know anything about quantum computing, but to play the game. Anyway, so with that, I'll close my lecture. I would say the big takeaway points I would like to press ahead is the theory of quantum estimation, quantum metrology, quantum detection estimation theory. These provide a very powerful tool to quantify fundamental limits of precision. And sometimes they give you some hint at designing optimal systems, sometimes they don't, but knowing what is the fundamental limit gives you a benchmark as to where you are currently and how much gap is there to close. And then one other important thing I would say is, well, I'm an engineer, all my degrees are in electrical engineering. I by no means I'm a physicist. I'm still learning from my physicist friends. But one thing I have seen is that there is a lot of intuitions, algorithm techniques, and tools from various classical fields, from information theory, machine learning, signal processing, digital communications, optical sensing, optical imaging, control theory. All of these will be necessary to be brought to bear along with the theory of quantum optics to really make disruptive progress in this field. That I'll thank my group members and happy to take any questions.
Thank you. Thank you, Saikat, for this fantastic talk.